I guess you could say. And my name is Toby Schnars, certified SolidWorks expert, old pro when it comes to SolidWorks Live. I've been on the other side of the interview in the past, doing demonstrations myself, but this time I get to actually host and talk to all of you. So very excited to be here with our special guest today, Omar. Omar, how are you doing today?
I am doing great, Toby. No place I'd rather be than online with you.
Well, I gotta say, I completely agree. No place I'd rather be than online with you. So, Omar, I know you come from a very strong simulation background. Maybe before we get into the actual demonstration today, you could just tell me a little bit about kind of how you got started. Did you get started in industry, or did you come right out of school and go right to work for Dassault Systems?
No, so I finished my undergrad from the University of Pittsburgh and actually went to work for Northrop Grumman
Nice.
in Baltimore for a while, right at the airport there, BWI. It's a really cool location because they actually share a runway with the airport. So it's at the time it was their electronic sensors and systems sector. So, if they were putting like new antennas on airplanes, they would put it on the plane and then they would take it up and do flights so you could get like vibration data during flights. So
Whoa.
that's kind of when I was in undergrad, I worked at ANSYS for a little while. I was co-oping, so I was kind of in the FEA space or analysis space for quite a while. And then I ended up going to get a master's. And
And for those in the audience who don't know, what is ANSYS?
so ANSYS is a finite element analysis software company that's actually based in Pittsburgh. It's grown quite a bit, but so when I went back to get a master's, then went to get a PhD, and when I finished my PhD, I actually went to work for ANSYS full-time out in California. And then about 11 or, geez, it's been a while, 11 or 12 years ago, I joined Dassault after ANSYS and, working with the SolidWorks simulation team. So.
And what kind of stuff do you do at Dassault?
So, it's been a really interesting time to be in the simulation space at Dassault, especially in the SolidWorks brand, because we are starting to work, and we'll talk about this today, but we're starting to work a lot more with some of the other brands. And one of those brands is the SIMULIA brand, which owns the Abacus solver. So I've actually, in the last couple of years, just been helping us with some of these newer products that we're introducing from SIMULIA. So, and we'll show those today. So just helping the sales team get up to speed with what we offer, helping R&D kind of develop these products, and working with our SolidWorks customers first and foremost.
As somebody who's used a lot of different tools to do FEA, what are some similarities that you see across like all FEA packages, and what are some differences that like maybe differentiate one package from another?
So I think what we're seeing, and the industry's really been going this way for quite a while, is the desire to more tightly integrate with CAD. I think for a long time there were requirements that you had to kind of build your model in the FEA software. And what you're seeing now is just a lot of packages are just kind of CAD agnostic. So whatever CAD package you're working in, whether it's writing out a neutral file or using the native CAD geometry, that's become really a driving force. You're also seeing like user interfaces just get more and more intuitive. Again, I remember oftentimes finite element analysis just the software was really difficult to use, and it's getting a lot easier. And just with computing resources getting so much more vast and powerful, the types of problems that you can solve are really just outrageous nowadays. So it's a cool time to be a simulation nerd.
And in the past, I would think that you would spend a lot of time probably coming up with workarounds when the system resources were not sufficient to solve the challenge that you needed to solve for. Do you see that also decreasing as computing power gets stronger?
Yeah, so I think inevitably people want to solve their full models as complex as possible. I think and that's certainly available now, and you have the capacity and the capability to do that. I still think good analysts will reduce their models where they can and make simplifications where they can, just to reduce runtime, especially early on, right? Because you don't want to be running the most complicated problem all the time. So when you're just in the design phase and really going through design alternatives, you make some simplifications, and then when you get to your final design, that's when you run the full complicated model.
I remember when I used to teach simulation classes, I would say it's this finite element analysis. That means it's almost like you've got a bucket of elements that you can throw at a puzzle, and that bucket is we're going to soon have the computing power to do that.
Yeah, I mean, especially, and we'll talk. I don't know if we'll talk about this specifically, but especially with cloud computing, right, which is one of the capabilities that we have with these products that are on the 3D Experience platform, right? So you're not limited to just running on your local machine, right? You can run on the cloud and utilize 18, 36, 144 cores to really speed up run times.
Yeah, I remember when I was doing tech support the first time I saw somebody who had a computer who had, like 16 cores on their local computer, and they had like 128 gig of RAM. And I was like, oh my goodness, like what are we moving into?
Yeah.
And now I'm sure that's going to become more and more commonplace. And like you said, with the cloud, it's just like the sky is the limit as far as how many resources you can access.
Yeah, and Toby, I just want to make sure I have like a beeping on my side. I think it's from the platform that we're using to broadcast this. I hope it's not coming across.
I'm not hearing it, but we can ask our chat for sure. And
Okay.
This is probably a good segue to say hello to some of the people in the chat. So Todd's in the chat. He says, "What's up, Dr. Oz?" And
Hey,
Dan is in the chat saying, "Hey, Toby. Hey, Omar." And Eric is in the chat saying, "What's up?" So we got lots of people out there in the chat saying hello. So we want to just say hello to all of you and thank you all so much for joining us for this SolidWorks live event. And if you guys have any questions for Omar throughout the presentation, feel free to drop them in the chat and I'll be sure to ask him live and we'll try to get those questions answered for you. So Omar, what do you have queued up for us today? What are you going to show us today?
So today we're really going to focus on doing what are called parametric design studies. So this, if you're a SolidWorks user, this is something that a SolidWorks simulation user, you may have done in the past. But what we're going to focus on is really doing it using the 3D Experience platform and the SIMULIA solvers, right? So, and still leveraging your CAD model, your SolidWorks geometry. So we're looking at a wood grinder here.
So just to level set here, I mean, when I would do, or when I envision a parametric simulation study in the past, I think what I would probably envision would be almost like a table of different criteria. And then I would adjust those criteria in the table and basically like one cell of the table might be the force. So I might apply like 500 newtons, then maybe like 1,000, maybe 1,500. Then maybe like the next criteria would be the, say the diameter of the shaft. And so I would adjust that to different parameters. Is that what we're talking about here when we say a parametric study?
Yeah, but we're not manually adjusting it, right? So it's going to be automated for us. So we're gonna specify kind of we're going to specify some of the geometric parameters and the range that they can go through.
Okay.
And then we're going to have some design criteria that we're trying to meet. So, we're going to try to ensure that our factor of safety is below or above a certain number, and that our displacement is below a certain number. And obviously, the objective is going to be to minimize mass from one of these parts, right? So
okay, so those design criteria are kind of like goals.
Yep.
So if you were doing a simulation study on a treehouse, you could say, I want this treehouse the goal would be to minimize the mass of the treehouse, but it also has to withstand a certain amount of force. It needs to be able to hold a certain amount of weight.
Absolutely.
So many kids jumping up and down.
Yeah. You
Okay.
don't want your kids plummeting through the ground of your treehouse, right?
And then what you get back in return, like, because normally when you do a simulation study, what you would get back in return would be like, this is how much stress you can expect. But it sounds like what you're saying is what we're going to get back in return is the geometry. It's going to tell us what the geometry should look like.
Yeah, so we're going to be able to see the stress, the displacements, the strains, the factor of safety. But what we're really looking for is that optimized geometric shape and configuration, and we can then kick it back to SolidWorks, right? So, that's the goal, right?
That sounds pretty useful. Yeah. That would save me a lot of time, because a lot of times I'm sitting there like manually doing that. Then I run the study, then I change the geometry, then I run the study again. Yeah, I could definitely see this saving people a lot of time.
Yeah. And I apologize, guys. I'm in a hotel room normally, and I'd have two computer screens up, so I'm not actually, I can't see our faces. I hope everything's coming in clear, and
it looks
you guys
great.
can hear me okay.
Yeah, it looks great, sounds great, and we can't see your computer screens either. So, we don't know if you have 2 monitors or 10 monitors. You could tell us you got 6 monitors in that hotel room with you. I know there's been times when I've gone to hotel rooms and I set up like 2 of my own monitors. I plug into the TV in the room also, and I'm like, running the space station.
Plugged into the TV. That's true. I don't think I have an HDMI cable, but I could have done that for sure.
Yeah, that's a pro travel move right there.
Yeah. I'm so out of practice from travel. I haven't done it in a while.
So at this point, I think we're going to switch over so that we can see your screen. And Eric has given us confirmation in the chat, says, looks great, Omar. And MT Engineering is here as well and says he loves SolidWorks Simulation. So
okay,
awesome.
Well, hopefully,
we're right there with you.
Yeah, absolutely. So let me know when the...
You're good. You're good. I can see it looks like... I don't know what this looks like to me. It looks like maybe like an old printing press or something.
Yeah, so it's actually a wood grinder, right? So the intent is the wood kind of gets fed in up here, and this thing can pivot depending on the size of the wood, and then it gets ground down.
Okay. I like it. I like it.
And what we're going to be looking at specifically is just one of the components, right? So this arm right here is kind of pinned at a couple spots. It's got a couple hinge constraints, meaning it can rotate. It could just rotate. It really can't move in the X direction, so back and forth. And then it's got kind of a known maximum load of, I think it's 2,800 pounds that gets applied to it. So we're going to kind of break that one individual part out, and we're going to go ahead and do some analysis on it. So
and maybe you can just highlight the arm you're talking about again. Just
so it's everyone this guy right here.
Okay, great. Okay, so we're going to find out what we can do to minimize the mass of that part.
Yeah, and so again, right, we're really going to be talking about the capabilities on the 3D experience platform and how you can leverage your SolidWorks CAD geometry and the parameters to kind of drive the design. So let me minimize or get out of the full assembly, and let's pull up the arm. So this is the arm we're going to be looking at. Again, it's got there are going to be a couple hinge constraints on these cylindrical faces here, meaning that they can rotate, around the hinge. We're going to put a constraint on one of these faces that says it can't move in the Z direction, so kind of normal to the face. And then there's going to be a remote load that's connected to these interior faces out at a distance of about 2,800 pounds. And so, Toby, I'm just going to kind of make the assumption that people probably haven't used a 3D experience platform and haven't kind of leveraged SolidWorks geometry. The integration between SolidWorks and the 3D experience platform has been getting stronger and stronger and stronger. So, it's very, very easy to just take this part, and you can see that I'm calling this thing revision A. A bit of a spoiler alert. There's going to be a revision B that we work on after we take a look at some of the results from Rev A.
Okay.
But really, you just kind of save this part to the platform, and then you can go ahead and open the part using any of the relevant apps. So in this case, we're going to be using the mechanical scenario app, which is just the SIMULIA app that we use to define our finite element analysis. So
you're saying you're right within SolidWorks here, but you're accessing the 3D experience tools over in the task pane, and that's giving you access to all the power of SIMULIA, based on what your company has.
Yeah, and so this can be a little bit busy. I apologize, right? Depending on what apps people purchase, right? That's what's going to be available here. And obviously, as an internal employee, we have access to a lot of apps. So,
sure.
But the one that we're going to be working in today is the mechanical scenario app. So let's go over to the platform, and that is right here. So this is, you guys can see that?
Oh yeah, that's looking great.
Yeah, so I pulled the model over. I don't want to spend a ton of time kind of going through finite element analysis, but this is a real simple setup, right? So we're using an alloy steel. There's a really nice kind of fully populated material library that comes with these tools that's got materials with fatigue data if you're doing durability analysis. It's got a full host of metal materials, some hyperelastic materials, and both with and without plasticity behavior, right? So you can see in this case, I'm assuming this guy is made of alloy steel, and I'm leaving the plasticity on. So if it does exceed yield, we would get some plastic deformation. And the other thing that you'll notice if you're a traditional SOLIDWORKS user is that we've got a brick mesh here. So, you know, one of the things that people who were using SOLIDWORKS often complained about on the simulation side was the inability to create brick, kind of swept brick meshes. And in finite element analysis, bricks can be a little bit better to use in some cases. Numerically, they're a little bit less computationally expensive. And you know, for a structure like this, it just makes sense to use the brick elements. So that there's a whole host of types of elements that are available in SIMULIA that you didn't get with SOLIDWORKS Simulation. There are also a whole host of material models and element types. So not just brick elements, but there are some element types that are specifically good for hyperelastic. There's reduced integration. So there's a lot of bells and whistles that are available with the SIMULIA solvers.
Yeah, I mean, I would say that even just what you've described so far, you know, normally if you're first getting into SolidWorks simulation, you learn that you can deform a piece of geometry to the point of yield. And as long as you don't exceed that point of yield, it will, in theory, return to its original shape. But once you go beyond yield, kind of all bets are off, and now you get into nonlinear studies and some pretty advanced stuff. But it sounds like you're saying that a lot of that is just accounted for right out of the gate with the 3D Experience library, because plasticity is included as part of the material definition for some of these materials. Is that right?
Yeah, absolutely. And, you know, anybody who's doing finite element analysis, I'm sure, has heard of the Abacus solver. That's the underlying solver that we're going to be using here. And this model that we're looking at here doesn't have contact, but there are just a lot of like really niche things that the Abacus solver is very, very good at. Explicit dynamics is one of those things. Complicated contact modeling. So, you know, with SolidWorks, where you might have to go specify a bunch of contact pairs if things are coming into contact, you don't have to do that. So it automates a lot of that, whether it's plasticity behavior or contact. There are just a lot of things that are automated to make this a lot more user-friendly for more advanced types of simulations.
And even with regards to the brick mesher, I mean, with a tetrahedral mesher where you've got, you know, four-sided element, we would normally say on a thin model like this that you really want to have like 3 or 4 elements through the thickness. When you're using a brick mesher, are you able to get away with only having 2 elements through the thickness?
Yeah, you can get away with 2 or 3. And there's also some element formulations that would allow you to even get by with 1. In a case where you've got bending. So there's, yeah, the brick elements allow you to get away with a little bit less through the thickness than a TET does. Now, the downside of bricks, right, is here, the upside of TETs is you can mesh any generic shape with TETs and just fill it in. You can't do that with bricks, right? So there are situations where both of them make sense, and you know, you can mix and match here. Not if you had an assembly, not everything has to be modeled with bricks. You can have parts modeled with TETs, parts modeled with bricks, and everything kind of works together.
Well, that's great. I see that SHAD in the chat was asking about, so, you know, some of the benefits of the brick mesher over the TET mesher, and so I think you did a great job of conveying that. And I think it also is, you know, just a nice opportunity for us to remind all of our SolidWorks friends out there that, you know, one of the big advantages of 3D Experience is that you get everything that you're used to in SolidWorks. You saw that Omar had that beautiful SolidWorks assembly up and running, but then you're able to augment that with some great new functionality just by being able to hand off, you know, right within the task pane in this case, to 3D Experience. And so now you're opening up the doors to all these amazing tools that you're not going to find in SolidWorks, that you're only going to find in SIMULIA, just by doing basically a right mouse button save in the task pane and getting to that new set of tools. So I think it's always important that we share some of the things that we've discovered so far about 3D Experience in that context of like, we can do a lot in SolidWorks, we can do a lot in simulation, but we can do even more in SIMULIA. And here's just a few examples of what some of those things are. Yep,
absolutely. So you want me to walk through this setup a little bit more, Toby?
Yeah, I mean, I think that, you know, in my experience, the first thing you do is you assign material. I think you've covered that you've assigned material. Next thing you would do would be to set up the fixturing for it, right? Have you already set up the fixturing for this one?
I have, yeah. And we can just kind of walk through that. So I've set up my scenario, and like I said, let me just highlight a couple of these. So there are a couple hinge constraints, and you can see the face is highlighted in blue here. So there are 2 hinges.
Now,
There is a
is that gonna, how many degrees of freedom is that locking down when you assign that hinge restraint?
So for solid out, it's basically locking down all the degrees of freedom except rotation. It can only rotate about this face.
Okay, got it. No axial translation, no deformation of the nodes on those faces, external from the axis.
No, right, exactly. Yep.
Okay.
And then really the only other important, well, I mean, there's a fixed, let me back up here. There is a fixed displacement on one of these faces. So there's a constraint that's basically saying this face has to remain
coplanar.
flat. Yeah, right.
Okay.
Exactly. And then we just have our remote force that's applied to these 5 or 6 faces that cut out at the bottom. And it's about 2,800 pounds. You can see it's been converted. We're working in the metric system here, so it converted it to newtons, but that's about, I believe it's about 2,800 pounds. And we can see the direction of that force.
Is that fixed displacement on that planar face? Is that because this thing is up against a wall, or
Yes.
what is that simulating?
Yeah, so it's up against some components that are gonna hold it flat.
Okay, got it.
And
Okay.
really, that's it. So then we can go ahead and run this. And for the sake of time, I didn't want to. I have the results here, so let's just pull up some of the results, because once we see the results, it'll make kind of more sense what we kind of what we do next and what we decide to do. So here is our von Mises stress, and the first thing that you notice, right, is that you've got this area that's really blue, so really, really small stress values throughout the center of this guy, right, as compared to out on the edges. And von Mises stress is one way to look at that. I like to look at factor of safety for a situation like this. So we can see the minimum factor of safety is about 7, and it's here at the corners. Anything that's in gray, it looks like gray to me, is a factor of safety above 20. So I'm only showing the contour range from whatever the minimum is up to 20, and anything that's gray is above 20. So right away, we kind of know this thing is over-designed, right? We can also look at the displacement, really small displacement of about, the maximum displacement is about 1.3 millimeters. And these are just the pre-populated, like it automatically shows you von Mises stress, but sometimes people want to look at principal stresses or, axial or directional stresses like sigma X, sigma Y. So all of those are available. I shouldn't say most. It just depends on the type of the industry that you're in. But a lot of times people are most interested in von Mises stress. So that's the one that gets plotted by default. But anyway, okay, so now we've run this guy. We can see that it's really over designed, right? Like a factor of safety of 7 is just way too high for something like this. You could probably get away with a factor of safety of 2 or 3, right? And because we can kind of see, if we look at the von Mises stress, this area here of low stress, a real simple thing that we could do to reduce the weight would be to go back to SolidWorks.
See, and this is what I would do, is I would end up going back into SolidWorks and like trying to sketch that same shape, right? Yeah. And then just like remove that shape, right? Just try and get it close, and and then I have to set up the whole study again and run it again.
Yep. So, and we don't, so what's nice is we don't have to do that here, right? So I'm going to go to my revision B.
Okay. There's a little bit of data management in the cloud here.
You're absolutely.
One revision for another.
And you can see what I've done is I've added a slot.
Okay.
And the slot has a couple parameters that we can vary, right? One is the width, one is the location, which is the how far down it is from the top, and the other one is the length, right?
Okay.
So I kind of guessed at what the width, the location, and the length should be as an initial. And what I'm going to do is I'm going to run a parametric study and vary those to see which one meets my design criteria while also minimizing the mass, right? So we got my Rev B now. Again, I would do the same thing, kind of kick this up to the platform. It's going to know that it's a revision B. And what I can do with, after I've run this analysis is there's a way that I can say, look, I want to create a new revision of this analysis, and it will, make all of these Bs, and then I can just replace it with my B revision. So let
Oh,
me,
wow.
yeah, so I don't have to really reset up the model. I just kind of copy that A rev to a B revision. So let me just pull up the guy.
Yeah, I could definitely see that saving time.
Yeah, tons. So, and I can, obviously, I've been using these products for quite a while. So I have a lot of models here in my space, but I can filter it down to, to my simulation content. And you can see if oops. So that's my Rev A. Oh, crap. Sorry, guys.
Oh, all good.
I swear I've done this before.
It's all good, man. And, this is interesting. So ultimately what you're saying is that you're going to be taking those parameters that you specified, so like the slot width and the slot location and the slot length, and then you're going to be essentially pinning them against some design criteria. I mean, can you pin that against like factor of safety?
Yeah, absolutely. So basically, you flag any criteria that you have to meet. So for a structural analysis, it's going to be things like factor of safety, displacement, stresses. It could be frequency. So if you could run a vibration analysis. It could be temperatures if you are running thermal analysis. It could be a combination of those, right?
Oh, so for like a temperature one, you could figure out what the optimal wall thickness is in order to prevent certain temperature from getting through, or for the insulation purposes.
Yep, absolutely.
Wow,
so
that would be helpful.
Let's pull up. So again, all I've done is I've replaced it with a revision B. I don't have to reset up. Oops. I don't have to reset up the simulation. I just basically go ahead and run it. And use this real quick.
So maybe while this is running, maybe you could just address real quickly, what's the difference between this parametric design study and a generative design?
So a generative design would be doing like at least when I hear that, I think topology optimization, right? So where you're really not as constrained by geometric parameters. So like the way you're just kind of saying in this space, this body can reside. Here are the forces it's going to see, and come up with whatever shape you can to meet the criteria, right? So.
Yeah. Okay. So yeah, I think I've seen them before, like where they'll say, I want to make a bracket to hold up a shelf, and then that you just say like it's held here and it's held here, and then it creates it looks like almost an alien structure that's holding it up, like a super crazy freeform structure that's holding it up. That's the result that you get from a generative design, right? But that's not really what we want in this case, because in this case we're a lot more constrained, because this is a piece of machinery. It's one piece in an assembly. It has to fit in with other pieces. So in this case, it would be more appropriate to do like a parametric design study.
Absolutely, yep. And I'm just gonna solve this again. It looks like sometime in the last day or two when I was working on this, the data for the simulation got mismatched from the actual SolidWorks model. So this is great, though. You guys can see exactly how long it takes. So all I've done is I hit update, which just updated the mesh to reside where the geometry is. It looked like they were mismatched a little bit. And now this is what so right out of the box, first of all, you can solve on 8 cores with these products.
Okay, I like that.
Yeah, and those 8, you can run that locally, or I can run it in the cloud. So, if you don't have 8 cores on your machine, or maybe your machine has 8 cores, but it's a little slow, or you just don't want to take up the computer resources on your machine because you want to do something else. I can just say, look, I want to run in the cloud, and I've got the ability to do that, again, on 8 cores, default out of the box. And then if you wanted to run on more than 8 cores, then you would have to buy computing credits or tokens. But and this is a way to really, really speed up your simulation times, especially for complicated models, right? for a model like this that's not super complicated, kind of just a linear analysis, you're not going to get a major speed up. But man, if you're running an explicit dynamics analysis or a really complex nonlinear analysis, running it on more cores is really going to speed it up.
Yeah, running on that entire assembly. So
Yeah.
I got excited when I saw that 144 cores. So what you're saying is that, you know, anybody who gets this product, you get access to the 8 cores, you're able to do your solving, you know, it's all good. But if that's not enough for you, we do have options to help you upgrade to get access to more cores.
Absolutely, yep.
Okay.
So I just fired this off and asked it to solve again, and you know, within 30 seconds, 45 seconds, this thing is going to run. And again, I'm running it locally. Now, the assumption with these solvers is that everything's nonlinear. So, if you've used SolidWorks Simulation in the past, you know you can kind of control the times or the stepping in a nonlinear analysis,
Mm-hmm.
but. You can do the same thing here, but I think I'm just asking it to solve it all in one step. This is a pretty simple analysis here.
So what you're saying there though is that like when something solves as a nonlinear study, you're assuming that time is a factor. Is that what you're saying there?
So with nonlinear, there's kind of a pseudo time, right? So time represents kind of percent of load application. So a lot of times with nonlinear analysis, because it's path dependent, right? It's not like if you apply 100% of the load all at once, it's going to look very different than if you apply 10% of the load incrementally with a nonlinear analysis. So you know, the response is just not linear. So
got it. Okay. So then you have the ability to,
like a time of one. We're not really running this in a transient nature. A time of 1 second just means 100% of the load has been applied.
Right. Okay, I got it.
All right, so yeah, okay, so here's our results. You can see the I don't know if you guys remember, but the displacement I think was about 1.3 in the model without the slot. But we could look at, you know, von Mises stress. We can look at factor of safety. So you can see my minimum factor of safety now is down to 3.07. But basically what you do is, so you run your parent study, right? This is the model that I want to do a parametric study on. And there are a bunch of sensors that get created by default. And these sensors are basically what are used in your PDS study, your parametric design study, as design variables. Now, also, there's what's called a parametric bridge. And you can see that's where my location, my width, and my length. So any parameters that I set up in the SolidWorks part are going to be ported over here. And this is, you know, this is basically what I'm going to be running my these are the parameters I'm going to be using to run that parametric study.
Sure.
And you can see I've got sensors for for factor of safety, you know, the minimum factor of safety, my displacement, my maximum displacement, and there's also a mass sensor, right? So those are the three that I'm really going to be focusing on when I run my parametric study. Okay. So again, you run your first analysis, and then you create what's called a parametric design study. So I'm just going to come back. So these are, again, I don't want to get like lost in kind of some of the minutiae here related to the platform, but these are the different apps that you're going to be, what's going on here? Sorry, guys. That you're going to be hopping through. So there's a modeling app, a meshing app, and then in the scenario app, you can see there's a parametric design study. So I'm just going to activate that parametric design study. I've already got this guy set up, so let's talk a little bit about it. I've specified what my design variables are, so you can see for location, for width, and for length. I'm specifying the min and maximum, and I'm putting in a step size. Now, you don't have to put in a step size. If you don't put in a step size, it will just, you know, randomly look, not randomly, but it will kind of take a guided approach to looking between your min and max values.
Okay.
But oftentimes, you know, it's not like you're going to build something and want it to be 2.1375, the location to be, right? Oftentimes you want it to be like whole numbers.
Yeah, like in this case, it's going to, you know, maybe it'll start in the middle. So maybe it'll start at like 3, and then it'll go down to 2.75. Then it'll go up to like 3.25, then 2.5, then 3.5, and like kind of figure out what the optimal, you know, I guess it's going to be doing a combination of all 3 of those variables.
Yeah, absolutely. Yep. So you've got those 3 input variables. Then my response variables, I'm just pointing to those sensors, right? And what I'm saying is like, look, I want the minimum factor of safety to be 3. I'm not going to
Okay.
limit what the max is, but there can't be a value under 3 or else the design is not feasible. And I'm also saying that I want the maximum displacement to be less than 3 millimeters.
Okay.
So those are 2 design constraints, right? If any of the runs don't meet that criteria, then it's going to tell us, it's going to highlight it in red and say that they're not feasible. And then the goal is to minimize the mass, right?
Exactly. Let's get this thing as light as possible.
Yep. And then in our simulate tab, like we could specify how many points we're looking for. So in this case, I told it, look, run 50 points. And let's take a look at the results.
Looks like you might have to run it again.
No. That would definitely take way too long.
Got to bust out that 144 core credit.
Yeah, so here we go. Yeah, so this kind of interface comes up as you're running this simulation. So, and it's very, very cool. So you can see here are my 50 points. So, and we're going to configure this a little bit, but so there are 37 points that were considered feasible. That means they meet our requirement. And if I click on any one of these, so let me just click on one and go to.
The slot changed. I saw it.
Yeah. So, if I click on any of these, I'm going to have the results that I'm interested in. So up here, you can see it's changing. It's showing me what the maximum displacement is, the minimum factor of safety, my design variables, what they're set at. And I can walk through and take a look at, all of those plots that were, yeah. So here's my factor of safety. I can see my minimum factor of safety is 3.44. So those are for all the runs that are feasible. Now, if I click on any of them that are infeasible, one of these response variables is not meeting the criteria, right? So I think I said I want my minimum factor of safety to be 3, and this is only 2.5, right? So, and then
what's the difference between that and failed?
Okay, so failed means that there was a problem with the geometry update. So, maybe it was deleting a face, or the width, or the width was too big. So like one of these faces went away. So those ones, yeah. So failed is different than infeasible. Failed means something happened and it didn't actually run the simulation.
Because some combination of those dimensions at their maximum ranges caused it to like blast the whole face off or something like that.
Yep.
Okay.
And then there's infeasible, which means it didn't meet one of the criteria. Feasible, it meets all the criteria, and then it highlights what it feels like is the best.
Okay. Let's see it.
So
it's the big winner.
So design number 1, the weight was about 61 kilograms. I think in the original design without the slot, it was 66 kilograms.
Okay.
So yeah, design 1 with the initial slot 61 and then down to 58. So that it's cutting 5% of the mass out just in the slotted configuration, which if you're making a bunch of these, it matters, right? And the other thing that's really cool is, so right now the x-axis here is just the run ID, not really useful, right? Like you don't care if it's run number 1 or run number 50. So what I can do is I can change that x-axis to, let's do maximum displacement.
Oh, wow.
And then you can see, right, so here is basically anything over here, it fails because the maximum displacement is too high. And then I can change my y value to something like mass. So it's cool, right? You can see all these guys that are red are failing.
And you can see generally as the mass goes up, the displacement goes down. I mean, which for this one single variable we would expect, but I could see there being other studies where that would be super insightful.
Yeah. And now I'm plotting maximum displacement and minimum factor of safety, right? So here, these guys, this is the red zone, right, where it's violating one of those two, or here where it's violating both.
Mm-hmm.
And then here's our ideal point. And then on top of that, right, so again, like I can walk through any of these. I can right-click on any of these and say, look, I want to add that to my favorites. If I want to like compare a few of them, maybe maybe this is just a little bit too close to the displacement or the minimum factor of safety, right? It's super close to 3. So maybe I don't want to use that one. So I can flag a bunch of these. I can also say, look, I want to generate an alternative. And what that will do is it will actually, I can add a prefix. So this will actually generate that geometry that I can open in SolidWorks. And then if I wanted to, I could actually replace the part that's in the assembly with this optimized design, right? So really powerful technology. And again, all integrated with SolidWorks, right? So really easy for me to go and push these changes back to SolidWorks. If I make a change on the SolidWorks side, it's easy to push those changes back up to the platform.
So at this point, I think this is what you just said a moment ago. I just want you to reiterate, at this point, now that you've got that design, you've determined which one is the best, what does it look like? And you don't have to necessarily do this. You can just kind of talk me through it. What does it look like to then get that geometry back into SolidWorks?
So that's what's going on right now. So you just right click on the design you're interested in and say you want to generate an alternative.
Okay.
And that will generate so it's called a physical product on the platform, but that physical product can then be read back in to SolidWorks. And we could replace the existing arm with this version of the arm.
Right back into the assembly.
Right back into the assembly, yeah.
Wow. Yeah, I could definitely see this being a huge benefit. What do you guys think out there in the chat? You guys think this is pretty impressive? If you like what you're seeing so far, be sure to give us a 1 in the chat. We'd love to hear your feedback. And of course, be sure to like and subscribe to this channel. Like this video, subscribe to this channel, but let us know in the chat if you're enjoying what you see here. If you think you could find a use for this type of technology, give us a 1 in the chat. We'd love to hear your feedback. And of course, any questions that you guys have, feel free to put those in the chat as well. We had a question from Brian earlier. He was asking, a little bit more about what's the difference between the brick and TEP mesher. I think he did a great job answering that. And Eric is very impressed by 144 cores. Says more power to the shields.
Yeah. And what's great about the SIMULIA solvers, right, is they're really written to take advantage of multiple cores. So, the SolidWorks simulation solvers, you could throw as many cores at it, but you can utilize as many cores as you have on your machine. But after about 6 or 8 cores, you really start getting diminishing returns. But with the SIMULIA solvers for large models, like, if it's taking 20 hours to run on 1 core, if you throw 20 cores at it, it's going to take about an hour. Now, there's a little bit of time that you lose when it's breaking up the problem to kind of run on those 20 cores. But in general, the solve time is going to be very linear as you increase the cores.
Okay, that's good to know for estimating, what's the appropriate amount to select.
Yeah, and I'm only showing, this is just an example of structural analysis. You can also do this. There's fluids packages available if you're doing CFD that can also take advantage of this to do parametric design studies linked with SolidWorks. There are also, again, like I said, it's an interesting time to be a simulation person in this space. We're starting to interact more with the EMAG groups, with so there's some EMAG products on the platform.
You're saying for
on the platform, yeah.
Radio magnetic frequency, that type of stuff. Is that what you're referring to?
Yep, absolutely.
Looks like Ramesh is saying hello. He should be watching this, right?
Sorry about that. I should have turned off my Skype.
So, what with regards to that, because it's just interesting you said that right when the question came in from Brian. He said, "Can you use like multiple different physics engines to come up with these design constraints?" So, can you, like for example, could you do a flow type of study and a structural analysis and have both of those be constraints in the same parametric study?
Yeah, so great question. I think right now, unfortunately, they have to be separate, but that is definitely a capability that's coming. So if you could have multiple structural analyses that kind of dictate. So, oftentimes you'll do like a frequency analysis and have a frequency constraint. Like you want to make sure that the minimum or the first natural frequency is above a certain value. And then you could couple that with like structural, like a factor of safety, displacements. And even
That's probably
thermal.
something like what you described in, at the beginning of the show, one of your first jobs. If something's up on an airplane and the airplane's vibrating at a certain frequency, you're going to want to make sure that your structures avoid that frequency. Is that
Yep.
kind of what you're talking about?
Yep, absolutely.
Okay. So frequency analysis could be combined with structural at this point, because that's all the same
they're all kind
solver.
of in the structural domain, right? So even
Okay.
thermal analysis, as long as you're using the finite element analysis, the FEA solver, all of that could be included. So if you, so thermal, as long as there's no fluid, thermal analysis, structural analysis, and frequency analysis could all be combined, because that's all kind of in the same software engine, right? You're all doing that in one of these structural products.
And what would be a scenario where you would use all three of those? I'm just gonna throw a curveball at you here, like off the top of your head. What might be a real world scenario where you'd be doing all three of those, where you'd be doing thermal and you'd be doing frequency and you'd be doing structural?
So potentially like maybe a circuit board.
Okay.
Because a circuit board, you're definitely going to have vibration concerns, especially like think of a circuit board that's in a computer, right, where you've got fans that are cooling it down. So that could have vibration concerns. It would also have thermal concerns, right? A lot of times if you're doing a circuit board, you probably want to run it in a CFD package. But as a first cut, you could certainly run it in a structural analysis package and look at like maximum temperatures on some of the chips that you don't want them to exceed. And then also look at kind of thermally induced stresses, right? So as those components are being used, is the board going to flex so much that it could potentially pop a component off that's welded?
Excellent answer. Excellent answer. Cool. So where do we go from here?
So, I mean, like I said, right, the integration with SolidWorks is getting more and more powerful, and we're getting more and more capabilities. So, again, this was just an example of a structural analysis. You could do it with flow analysis, and we're gonna see more and more of those types of capabilities.
Well, I can't wait to see what comes next, and I guess that's probably a good place to start winding down. I mean, I want to thank everybody, of course, for tuning in to the chat, and let us know if you have any other questions. We do have a few extra minutes here at the end, so if anybody does have any additional questions they want to ask us, I don't know, Omar, if there's anything that comes to mind that you want to show, feel free to interrupt me.
Yeah, I guess so. What I was gonna say is, you can see I told it to generate that best design.
Mm-hmm.
Or the design alternative, and I added a character string, just best design at the front of it, so you can see what it did. Let's open this. So it actually goes and it runs it sets up the simulation, because you only have access to those predefined results in the PDS study. So if I want to get like a little bit more granular look at that specific design, it actually creates a physics simulation, so an FEA model for that particular geometric configuration.
So you're saying it only generates that FEA model, or it generates that and the geometry we need in SolidWorks?
It generates the FEA model. It also generates the model in SolidWorks, right?
Okay.
So
great.
Yeah,
you can tell I have a real bias to SolidWorks. I just want to get everything back into SolidWorks. It's all I care about.
Yeah, so let's go back to SolidWorks. It should be. I haven't tested this. It's always nice to just do things on the fly. Let's just make sure that we should be able to just, let me close these guys.
Okay.
And we should be able to just look in that space. So let me just try to find it. All right, so best design, physical, we just want to grab that physical product. I think it's this guy, and we'll just drag it into SolidWorks here. And with any luck, this will be the optimized.
That's looking pretty good.
Yeah, so this is the optimized design. Yeah, so it's really easy to, everything's kind of working together as you'd expect, right? It's just nice to see this integration between a lot of the great brands that Dassault has, right? And, the SolidWorks and SIMULIA brands are just two great brands. So it's really nice. Man, I'm just having a lot of computer problems.
It always happens when you're presenting,
Yeah. Friday, that's tomorrow. Okay, that's fine.
That's fine.
Yeah, it's just nice to see that level of integration between, these great brands, like I was saying. And, if I were as a SolidWorks user, I feel like we were just doing a huge disservice to them by not really offering some of these more advanced simulation tools and capabilities. And we're just getting more and more of that stuff available for SolidWorks users. So it's a really exciting time to be in the simulation space.
Well, I gotta say thank you so much, Omar, for sharing this with us. Jan said something in the chat. He says, "Great job. I always learn something new." And I feel exactly the same way. I learned so much from watching this today. And I think that, one of the things that I always learn when I'm looking at a 3D experience presentation is just how much we can still do in SolidWorks, but then how much we can gain by leveraging some of the tools that are available to us now in 3D experience. Like in this case, so much of what you showed us there is either not available in SolidWorks, or it would just take so much manual labor. Like imagine generating a report of all those different plots in SolidWorks. You could do it, but it would take a lot of time, a lot of exporting the results to Excel and then making those charts and graphs, which I'm sure you've done before, manually. And it's great to see that we have all these tools available for our SolidWorks users who are ready to make that next step and really enhance and go beyond. Even it's hard to believe that there's things that SolidWorks can't do. But the more I learn about 3D experience, the more I learn wow, we could even go beyond what SolidWorks can do.
Yeah. It's all about having more tools in your toolkit, right? So, it's not about replacing SolidWorks or talking down at SolidWorks or SolidWorks Simulation. It's just, there are things that it's very good at, and there are things that it struggles with. And if, we can get a tool to help us with some of the things that SolidWorks Simulation struggles with, why not, right?
Yeah, exactly. And if that means you're going to be able to get your studies done that much more quickly, you're going to be able to leverage the cloud computing power. I mean, I think that's really what it's all about, because that's going to allow you to get, your designs out for physical testing that much sooner, get your products out to market that much faster. I mean, that's really what it's all about. So I'm so impressed with some of these capabilities, and just want to say thank you again, Omar, so much for being a guest today on SolidWorks Live Design.
Yeah, well, it's always fun. Always good talking to you, Toby, and working with you guys. So, hopefully we'll have some more opportunities to showcase some of the new simulation capabilities that are coming.
Yeah, I can't wait to see the next one. So I want to thank everybody in the audience today. Thank you all so much for joining us in the chat. Be sure to like, be sure to subscribe, and we're going to have more episodes of SolidWorks Live Design coming up in the future. So be sure to come back and tune into this channel, and let us know in the comments or in the chat if you have any suggestions for future episodes. We'd love to hear from you. We'd love to hear what you'd like to see. But otherwise, we will see everybody in the next one. Bye-bye.
All right. See you guys.